1.4, let's take a look at that. The approximation method of Euler, or Euler, however you want to pronounce it. I think it's Euler, but method of approximating solutions to initial value problems for first order differential. So the basic form is going to be y prime equal to f of xy, where your initial condition is y of x naught equal to y naught. Call that equation 1. So here's the setup. Assume and assumptions. Assume that form 1 has a unique solution phi of x for x not in some interval. Then this is the kind of the interesting way of looking at it. We're going to have like steps as we enter values. So let h be positive. It's like a small positive number. That's called the step size. And consider equally spaced points that you'll basically substitute in. So your equally spaced points will be x sub n, and this symbol means defined to be. It's kind of new to me, actually. I've never really seen that before, but so that's defined to be, right from the book. So we'll use it. Sounds good. So x sub n is defined to be x naught. So your like initial value plus nh, where n is a whole number. N is equal to 0, 1, 2, etc. Then you look at the tangent line, just like Newton's method, where you end up basically doing a derivative in the tangent line kind of thing. Well, similar. So for this one, for this method, the tangent line to the solution curve, so to the solution curve, is given by y equal to y naught plus x minus x naught times f of x naught y naught. So then, using the tangent line to the approximation of phi of x, we calculate the next iteration, which would be x1. So let's write that down. So using the tangent line to, where was that? To the approximation of the phi of x, we calculate the next iteration would be x1 is x naught plus h. And so then you calculate that. Phi of x1 is approximately y naught plus h of f of x naught y naught. And then you do that again. So then that gives you your x. So then your x2 will be approximately y1 plus h of f of x. Oops, don't need that parenthesis there. F of x1 y1. And you keep going in that manner. And so what you end up with is this recursively. So this is recursively defined. So this is kind of a dot, dot, dot. But then you could look at this recursively. And you get that x sub n plus 1 is equal to x sub n plus h. And then y sub n plus 1, so like the next term, right, is y sub n plus your step size f of x sub n, y sub n, where n is a whole number, like that. So I just need you to know just the basic form, nothing fancy here, just going to be able to evaluate one question. So to illustrate this, let's take a look at number 6 in the book. So for example, number 6, this is on page 28 in Nagel 9. That's more for me than you, so I remember what book I'm getting these out of. So number 6 says, and let's see, I'm going to go ahead and copy it over. I think I have it over here handy somewhere. I think it's here. Okay, so I have a lot of this worked out already, obviously. Okay, so I'm going to copy that over. Not the best way to do all this stuff, but it seems to be okay. All right, so there's my question number 6. So, use Euler's method, step size, to approximate the solution to the initial value problem. Okay, so this is all given. And then, so here's your steps. They actually give you the steps right there, but if you didn't know that, you're basically given, this means x naught is 1, and y naught is 1, and then that's the step size. So you can see that calculation when you plug in the step size. That's what you're getting. Okay, so the step size, or x sub n, is given, but we can still show how it was calculated. Okay, so that's what this is. Okay, so there's 4 iterations. So this is x naught is this. This is x1, 2, 3, 4. That's what you end up getting. Okay, so I'll do a couple and then I'll just show you the result. So what you get then, oops, sorry, move that up higher. You get, I'll do it over here, x1 is then your x naught plus 0.2, which is 1.2. So that's given, right? Okay, so I don't have to continue with that. But then y1 is equal to y naught plus 0.2, and then times, this is where you would have to evaluate, y naught squared plus y naught over x naught. So you're evaluating that, substituting in the appropriate values, where y naught is 1, right? Y naught's given is 1. So if you evaluate that, you get 1.4. So then 1.4 is going to be your y2. So this, or y1, I'm sorry, y naught's given. So then you substitute back in for your y2. So for y2, you use 1.4. Okay, and then you do that iteration. So take a moment to try to do the rest. I'm going to go ahead and just copy it over, save some time. This is where, probably would have had you calculate this in class. Made sure we're all on the same page, what we're doing. Okay, but so pause that and then go back and make sure it makes sense. I guess that's okay. All right. So let's just show you. Here's your 1.4. Right, substituting 1.4, evaluating, get you 1.96. So your 1.96 is your y2, which you're substituting back in here for your y3, etc. So this is the iteration that you're doing. Okay. So these methods, you need to realize, were developed before someone even considered what a computer was. So a lot of these methods go back, hundreds of years, because there was no way to actually do these exact calculations. So now you just have, computers do these algorithms and calculate them. But as you go into programming, you need to know the basic concepts and ideas of how things were done, so that you can do the same thing. You got to build from somewhere, and these are those building blocks. Okay, so that's 1.4. That's it for chapter 4. Like I mentioned, 1.3, just take a look. I won't test you on it specifically, so just take a look at the homework. Okay, 1.4, I might have you do a problem, but just practice for your own sake and looking forward on other stuff we might end up doing. Okay?